This is Jimmy Dean, and this is a two-way chi-squared inference procedure. It's a different way to do it two-way. So the two-way chi-squared test is used to compare several population proportions, usually by making a two-way table that gives accounts for both successes and failures. The null hypothesis is that there is no difference among the proportions, so they're all equal to each other. And then the alternative hypothesis is there is some difference from one of the proportions, that they're not all equal to each other. Okay, so to test your null hypotheses, we compare the observed counts, which is the counts in a two-way table, with the expected counts, the counts you would expect, except for random variation if the null hypothesis is true. If the observed counts are far from the expected counts, then that's evidence enough against our null hypotheses. The expected count in any cell of a two-way table, when your null hypothesis is true, is your row total times your column total divided by your table's total. I'll show you an example here. So not this example, but in the next one. Your free throw, this is example 13.5 on 747 and 48. So Linda is a basketball player who makes 70% of her free throws. If she shoots 10 free throws in a game, we expect her to make 70% of them, or 7 of them. So of course she won't make exactly 7 every time she shoots 10 free throws in the game. There's a chance variation from game to game, but in the long run, 7 of 10 is what we expect. It is, in this fact, that the mean number of shots Linda makes when she shoots 10 times. Okay, so in a more formal language, if we have n independent trials and the probability of successes on each trial is p, then we expect n times p. Okay, so up above it would have been your p was 0.7 times 10, which would be 7. So if we drew an SRS of n individuals from a population in which the proportions of successes is p, we expect np of successes in the sample. That's the fact behind the formula of expected counts in a two-way table. So we're going to use that in just a second. Alright, so treating cocaine addictions, and this is example 13.6. Actually, it started on page, I think, 746, I think, but it goes to that. So chronic users of cocaine need the drug to feel pleasure. Perhaps giving them a medication that fights depression will help them stay off cocaine. So they did a 3-year study comparing antidepressant called, oh boy, that one, despermine, I guess, and lithium, a standard treatment for cocaine addiction, and a placebo. The subjects were 72 chronic users of cocaine who wanted to break their drug habits, and that's important, you guys. You have to want to do that. 24 of these subjects were randomly assigned to each treatment. Okay, so here are the accounts of the proportions of the subjects who avoided relapse into cocaine use during the study. Okay, so here they are. So 24 of them did despermine, and 14 of them had no relapse. 24 of them did lithium, and 6 had no relapse. And then the placebo, 4 had no relapse. Okay, that means there's, a lot of them had relapse. They went back to cocaine. So, okay, so let's keep going with that. So the sample proportions of subjects who stayed off cocaine are quite different. So the bar graph in the next figure compares the results visually. So are these data good evidence that the proportions of successes for the 3 treatments differ in the population of all cocaine users? All right, so here's the bar graph. See, now the despermine, obviously, these guys had more of a success because there was more of them that did not relapse, and then there was more of them that did relapse in the placebo ones right here. Okay, so recall, this is what we just wrote down. If the observed counts are far away from the expected counts, then that's evidence enough against the HO. And then our expected counts is our row total times our column total divided by the table total. So here's a two-way table with the rows and columns totals right there. So despermine, no relapse, and then so that means the other of the 24, these guys add up 24. So there was 10 of them that did relapse. Okay, so in the lithium there's 18 of them that did relapse. In the placebo there's 20 of them that did relapse. Okay. And so the totals are 24s going down here, and the totals down here are the number of relapses down there. So we'll find the expected count for the cell in row 1. So here's row 1 right here, the despermine, and the column 2 right here is right down here. The proportion of relapse among the 72 subjects is the counts of relapse, which is the 48, divided by the total, 72, is 2/3. Okay, so 2/3 is our expected counts right there. So think of this as P, the overall proportion of relapse. If your null hypothesis is true, we expect, except for random variation, that the same proportion of relapse are in all three groups. So expected count of relapse among the 24 subjects who took despermine is going to be 16, okay? Same with all the other ones, you guys, 24 times 2/3. So the expected count has the form of row 1 times column 1. Well, row 1 has total 24, and the column 2 has a total of 48. So this is 16 also, you guys. If you multiplied all that out and divided by 72, you get 16 for each one. So we calculate the expected counts for the remaining cells in the same way. So the other ones should have expected counts of 16, or the relapse right there. Okay, so these are the 16 right there. So no relapse, yes relapse right there. Okay, those are the expected counts right there. Okay, these are the observed counts. All right, so because 2/3 of the subject relapse, we expect 2/3 of the 24 in each group to relapse if there are no differences among the treatments. Okay, so in fact, the despermine had fewer relapse, 10, and more successes, 14, than expected. The placebo had fewer successes, which was only 4, and more relapses of 20. It's another way of saying that the sample proportions in example 13.4 say that more directly that the despermine does a much better job than the placebo. So as long as it's a lot better, then we can reject our null hypotheses.